This is lecture 18. Okay, so according to the schedule, lecture 18 supposed to fall on Friday. Friday, because last Friday was on leave. So this is lecture 18. And the replacement for last Friday, so it will be tomorrow. Please take note. So the replacement already indicated in the Teams, the replacement for the last Friday, 6th of June, will be tomorrow, 12th June, from 5:15 to 6:45. So I know some of you all have your practical session up to 5 o'clock. Okay, so we will start at 5:15, but I will be here at 5. So we will start at 5:15 up to 6:45. And during the lesson tomorrow, I will return your quiz paper for you to check. Then you need to return it back to me. So maybe when you come in tomorrow, okay, later I will tell you how do you need to like sit down, okay, when you come into. So then it's easier for me to give out the scripts and collect. Otherwise, it is mixed all over. One, two, three. So here you have the pillar. Okay. So this is where you enter. Three area. Okay, so yeah, something like this. Copy. Okay, so you have three areas. So entrance, you are either from. Yeah, yeah. Okay. Entrance is here. So then we will space filling. So maybe here we have just go to, yeah, okay. Okay, so roughly, okay, so this is your sitting. Okay, so for when you come in for Thursday for replacement class, this is for Thursday. Replacement class 12 June from 5:15 to 6:45 p.m. So if you sit in this order, easier for me to distribute your piece paper and to collect. Okay, so otherwise will be too messy, so difficult to manage. So physical science 1, 2, then 3, 4, 5, 6, 7. Okay, so remember, take note. Okay, maybe I'll just take a picture later, then post it in your group. We cannot give a sitting order, lah. Just roughly you sit. So it's fine. Okay, let's move on to the continue with the session. Okay, before go to the next part here, which is involving radioactive decay, decay constant, and half-life. Just to remind you, okay, so we have, when we discuss questions from the chapter nuclear physics, we have seen a lot of values, numbers are given to a high precision. There is there is quite a number of significant figure values. So special case on significant figures for the nuclear physics chapter. Follow the significant figures that is provided in the question. When we talk about the number in the mass number, the nuclear number, the atomic number. So when you do the calculations, use the precise value that is provided in your data booklet or in the question itself. So option, okay, so typical rule, the final answers follow the smaller significant figures given in the question. This one you apply for the other part of your syllabus. We use the rule of thumb. Section B, leave the final answer in 3 or 4 significant figures. So this gives, when it comes to the final answer, then you can round it up. Okay, so give it to 3 or 4 significant figures. So this is applicable for the chapter nuclear physics. Okay. The other chapters, sometimes when you round it up, you probably will give it to 2 SF or 3 SF, depending on the significant figure of the raw values given in the question. Okay. So take note of that. Radioactive decay constant, and half-life. That's the, so we can see that we are halfway through the chapter. So in fact, this week we have 3 lessons. Okay, but on the Thursday's lesson, okay, there will be some time taken for the quiz papers to be written. That was one reason. Okay, I don't want to return the script last week during the lesson because then will be, I feel don't nice, drag too much. Okay, so at least I wanted to be halfway through the chapter 4 so that this week I'll be able to emphasize to finish it off. And I'm expecting, so I will finish a bit earlier and I can also start briefing on the last chapter. Okay, so as I mentioned, the last 2 weeks are allocated for the atomic physics, the last chapter of your for the course. So radioactivity. So what do we understand about the radioactivity? You have done the experiment on deciding about radioactivity. So based on your understanding from the simulation experiment that you have done, so how do you understood about radioactivity? And based on whatever earlier part of the chapter that we have discussed, so what is your overall understanding when you talk about radioactivity? So I'll just point to any of your case or to give me a explanation. Okay. Any comment? Why they have to decay over the time to reach the stable state? Okay. So the idea of radioactivity, it has to decay over the time to reach the stable state. And why it is not stable, we did discuss before. Some nucleus, when it is too wet, nucleus will not be stable. Yeah. And nucleus will not be stable. Unstable nucleus will be stable. So, but I cannot go too far. Okay. The unstable nucleus will decay. So, when a nucleus is unstable, yeah. When a nucleus will be unstable, we discussed about two things. The two processes will be nucleus will go through in order to decay. And it's based on the nature of the nucleus. Yes? One is when the nucleus is too small. When the nucleus is too small, it's not stable. So what will go through? It has to use to become larger. That's why you have learned about the fusion reaction. Correct? When the nucleus is too large also, it's not stable. So it has to reduce the size. So in order to reduce the size, it will break to smaller nuclei. So when it breaks to a smaller nuclei, it will go through what process? Fission process. So you have fission and fusion. So these two radioactive decay processes takes place in order for the nucleus to become stable. See, this is the same thing that can be brought into our life. When our life, okay, so when you talk about what we call our so the evaluation. Okay, so for when you refer to our body weight and height. Okay, so BMI, sorry. Okay, so there is a specific BMI. Okay, so for when you say a healthy person, okay, so the range will be for the male and also for the female. So if it's a person, okay, so the weight is for we can say for the teenage age, so about 20 years. Okay, so about 17 or 18. If their body weight it is below 40 kg, is that good? Not stable. Okay, not stable. Okay, so we will be very thin. Anytime when the wind blows across, okay, so the person can be flew away. Okay, so too lightweight also cannot. So over obesity, okay, so also cannot, because this is also like unstable. So they have to reach to a BMI measurement. That's the BMI measurement. So that depends on the age and so on. It will be calculated based on the mass and based on the height and so on. Yes. So it works for everything. It's not only for the nuclear. But when you talk about nucleus, then we will refer to the radioactive decay process. Okay. So when a nucleus is not stable, okay, so then it will go through a radioactive decay. So a random and spontaneous process in which an unstable nucleus decays into a more stable nucleus with the emission of alpha particle, beta particle, or gamma radiation, or gamma electromagnetic ray, gamma radiation. So that is what the radioactive decay process is about. When we talk about the radioactive decay, there is two types of the radioactive decay process. One is the random decay, the other one is the spontaneous decay. Sorry, I forgot to connect the writing pad. So we have, as I mentioned, so we have the random decay and spontaneous decay. So what is the difference between a random decay and a spontaneous decay? I'm not sure. Okay, so during the practical, okay, so I may have touched on it a bit, but I'm not sure about the other groups. So when you talk about the, generally when you refer to radioactive decay, there is two type of process. Fusion and fusion is the two situations, okay, so where the decay process can take place. It can be also mentioned as, I mean, it's a two situation, okay. But here, when you refer to the radioactive decay, it can have two type of process. A process may, or in a way, two type of process, or we can say it is due to two situation. So I will prefer to use situation. Otherwise, you'll get confused. Two type of process, we can fusion and fusion. So here is the two situation, okay, or two nature in a way. Yes, that will be even a better word. Two nature which influence the decay process. Okay, one is known as a random decay. The other one is the spontaneous decay. So what is the difference? So when we say a random decay, okay, so when I refer to a random decay, this is related to the unpredictable in decay, which nucleus going to decay in the next moment. So this is what more related to the experiment that you have did on the nuclear physics practical 6, I think, practical 5. Okay, so the simulation 6 or 5. 5. So the simulation whereby you use the online dice. Okay, when you what is that? When you throw and then finding the probability of the numbers, and then from that you calculate. So that is a random decay. Why we call it as a random decay? Because that is happens at a random nature. It is not influenced by any factor. Okay, it is not influenced. Okay, so by any, so it's random. So we will not know which nucleus is going to decay. Not all the nucleus. So for example, in this class, okay, so we supposed to have probably 200 and from 39, okay, you minus 230 students, okay, drop and all that. Okay, so I don't have 230 students here in the class, but okay, whatever number of students you have, not everyone is listening to me at this point. Very sure. Okay, so most following, some, okay, so may not concentrating, not focus. Okay, some is not here. So this is actually a random. Okay, so we have a sample of 230, but all these 230 have a different situation. So that is a random nature. So when you talk about in a nucleus you have nucleons. So nucleons are the protons and the neutrons. Not all of them will involve in the process of decay at one moment. So that is what we understand as a random decay process. So unpredictable in a decay process, which nucleus is going to decay in the next moment. It will keep on fluctuating. It will change. That's why when you did an experiment, you will not able to get a very smooth curve, but eventually the curve will decrease. Okay, so we have actually the outcome was the results was good. So it decreases, but there is a fluctuation involved. But you use when you sketch a smooth curve, but there is a fluctuation. So when we sketch the graph for the number of atoms versus the time. Okay, so you did number of times you throw lah. Initially, okay, it will start with a maximum, but as the time goes, it will decay. This is the fluctuation that takes place. So that will go on. So the fluctuation in the graph is actually refers to the random decay of the sample. Then from that, from n naught, okay, for the number of atoms to be reduced to half of initial, which is n naught over 2. This is what we understand as the half-life, correct? We learned that. The time taken for the sample activity. So I put the pocket pen so I can discover it. Okay. So not sure. So in this case, if you notice, so the time taken for the number of atom, or it can be referring to the activity, or it can refer to the number of mole of a substance to reduce to half of the initial. That is known as the half-life. Time taken for it to reduce to half of the initial. Then further, it will reduce to half some more. So n naught over 2 divided by 2, you get n naught over 4. It will take another half-life. Now the total becomes 2 times of the half-life. Then I have n naught over 8, 3 times of the half-life, and it goes on. Okay. So this is the graph. See, over here, even though there is a fluctuation, but you notice that the half-life, the time for the sample taken to reduce to half of the initial, it is almost the same, right? This is 0. Here, 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 here. Okay, later if I sketch. So it looks almost the same, right? So this is what the spontaneous decay is about. So the second type, okay, so which is mentioned here, spontaneous process. So the spontaneous process is a process whereby the nucleus is not nature, it is not stable, it has to go through a decay process. It does not depend on any factors. It is not triggered by any surrounding factor like temperature or pressure, okay, nothing. So it is not influenced by the surrounding factor. What influences it is the nature of the nucleus stability itself. So therefore, the nucleus is not stable. So spontaneously, it will go through a decay process. So that's why you can see the half-life is approximately the constant. Okay. So therefore, what is the evidence from the graph? Okay, take note. Huh? So evidence from the graph, when I see fluctuation, that is the evidence for random decay. The fluctuation is actually the evidence for the random decay. The half-life, which is approximately constant, that is the nature of a spontaneous decay. Okay, so note one for the random decay, the fluctuation in the graph is the evidence. And secondly, when you refer to spontaneous, half-life is approximately constant. So that concludes about the two type of process of random, two types of decay process. And when this decay process takes place, what are the emission particles that has been, what is the emission that is produced during the decay process? You have the alpha particle, beta particle, and gamma radiation. Alpha, beta is a particle. Gamma is a radiation. Okay, gamma is not a particle. Gamma is part of an electromagnetic ray. So we call that as a radiation. Take note. So I think before we came to this page, so I already give you a clear picture of random. So now, so random, every nucleus in a radioactive sample has the same probability to undergo a decay process. That is a characteristic. Spontaneous, the process cannot be affected by any external factor, such as chemical composition, temperature, or pressure. It is spontaneously is going to decay. Okay. So you can further take note of the graph. Those who probably came in late, okay, please check with your friends. What is this about? Okay. I don't want to go on to explain that again. So stable or radioactive. So how stable or radioactive? We did discuss about this. This is based on the ratio of the neutron-proton. Neutron-proton ratio for light nucleus, which is less, the proton number is less than 16. The stable nuclei have a neutron-proton ratio of nearly equivalent to 1. Anything that is less than 16 proton number, the ratio of, for the stability, the ratio of neutron to proton is 1 to 1. For heavy nucleus, so as it goes beyond 16, when the proton number is larger than the 16, neutron-proton ratio of a stable nucleus increases gradually. So no more ratio 1 to 1. So as the proton number increases, we need more neutrons to balance it up. So therefore, the ratio number neutron to proton will increase. So that will be easily understood by looking at this graph. Okay, I did when we discussed this graph before, isn't it? Did we? Okay, so earlier when we start, okay, so I have roughly told you about the stability. So when you look at this graph, when you go, you can go to 16. Okay, so around 16, you will find it somewhere here. You can see up to that 16, the ratio 1 to 1 between proton and neutron. It will be considered as a stable, because if you are looking at the line or the area, that area, the shaded area, or in fact the line that you see is a curve, n equals to z, that is a reference line. The line of stability is a line which curved with increasing gradient. So you notice that the gradient, it is increases, it is kind of getting steeper as the number of protons increases. So more protons, more of repulsive force. When there is more of repulsive force, we need to have more neutrons to balance the repulsive force by creating an attractive force. Okay, so that's why we need the more neutrons to come in. I think I have explained before. Okay, so I don't want to spend much time on that. So we can move on, you can analyze further on it. So that's why you can understand that when a nucleus is too large, it's not stable. You can see when the nucleus is too large, so we need to have more neutrons to stabilize. And this graph also explains the reason why the process of decay involves alpha, beta particle or gamma radiation. So when I refer to the nuclear reaction, so nuclear fusion, fission, radioactive decay. So when it comes to radioactive decay, so we need to understand about the particles that is being emitted during the process. So you have alpha, beta. So beta, there is two possibilities of beta. You have a beta minus and beta plus. Beta minus is the normal nature of the beta, which is electron minus. Beta plus is the abnormal one, we say, okay, so which is opposite charge, positive, and it is known as positron. The positive charge is a positron. The negative charge of a beta is the electron, normal electron. Then you have the gamma ray. Charges, you know, when you refer to alpha particle, the nature of the alpha particle, it is a helium nucleus. That is the nature of alpha particle. Nature of a beta particle, it can be an electron or it can be a positron. And gamma, okay, so it's a gamma electromagnetic ray. And then you can see information that is given for the mass value for the nucleus of a helium nucleus, for the beta minus, for the beta plus, and gamma. See, beta minus and beta plus, basically it is involving electron, but only one is positively charged, another one is negatively charged. So they have the same mass. So they have the same mass, no difference. But when you talk about the helium nucleus, helium, we can look at the details composition of the helium nucleus, 4 or 2. So the nucleus has 4, nuclear number is 4, and the proton number is 2. Therefore, if you want to find the mass of the nucleus, then it will be 4 multiplied by the unified atomic mass value. So when you multiply that, that gives you 4.001506. This is the nuclear mass value. Okay. So then gamma, as mentioned, is not a particle, it is a radiation. Therefore, it has no mass. So during a alpha particle decay process, so now we move on to discuss about the decay process involves alpha, beta, and gamma. I'm very sure you have done this before. Any of you all have no idea about the equations involved in the decay process involving alpha and beta. Any of you have not done this before? All have done, isn't it? Alpha beta particle decay process. So when you look at the alpha decay, so initially, okay, just say the initial before the decay process, I did mention before, we call that as a parent nucleus. So before the decay process, we call it as a parent nucleus. So the alpha particle, a fast helium nucleus, carries away most of the energy released in the decay process. What was that? Water bottle. Oh, okay. I thought somewhere the fire extinguisher fan. It sounds like some kind of a cylinder. Okay. So come back here. So the alpha particle, a fast helium nucleus. Yes, alpha particle is a fast helium nucleus. But in compared to the beta, alpha is slower. Because alpha particle only has a range of speed from 0 to maximum 10% of the speed of light. That is the what is being calculated. Okay, so theoretical value. The speed of the helium, the alpha particle. So it is about 10%, less than 10%, probably 9.9. Okay, so that is for the alpha particle. It's a slow. In a way, it is a slow. In compared to the other particles, it is slow. Beta particle is the one. Beta particle is the one that has the most range. So beta particle has the most range from 10% to 99% of the speed of light for beta particle, the electron. That's why when it comes to discussion about in quantum physics, the speed of the electron, okay, so sometimes we will sorry, we'll take it close to the speed of a light. We assume it is equivalent to the speed of a light. It is almost 99.9% to a most, but not equal to the speed of a light. The speed of a light, gamma ray, yes, gamma ray, it is a radiation. So that one, the speed is equivalent to the speed of a light. Okay, so after the decay process, you can look at, so before you have AZX, that is the parent nucleus. After you notice that the nucleon number has decreased by 4 and the proton number have decreased by 2. You can see the values here. So this is known as daughter nucleus. So after the decay process, the product is known as the daughter nucleus. The reactant is actually the parent nucleus. So the reactant, parent nucleus, the product is the daughter nucleus. So you notice the daughter nucleus, after going through the alpha decay, the nuclear number will decrease by 4, the proton number decrease by 2. Nothing much to further explain on that. This is a simple equation that you can write. So you need to know how to complete the equation when involves alpha decay. The principle that we use in trying to write the equation is we must understand the total nucleon number on your left must be equivalent to the total nucleon number on your right. See A, here A minus 4 plus 4, you get A back. Even when you talk about a proton number, total proton number on your left must be equivalent to the total proton number on your right. So Z minus 2 plus 2, you get back Z. Okay, so in any nuclear process, conclusion, the total nuclear number and the total proton number has to be conserved. Take note that. Okay, in any nuclear decay processes, the total nuclear number and proton number will be conserved. Even the energy also will be conserved. Energy before and energy after has to be same. Okay, but what will actually change is the neutron. The number of neutrons will change during a decay process. That's the only one will change. The nucleon number, the proton number, the energy. Okay? We don't just put it as energy, we put mass energy. So when you say mass energy mean, there can be a situation where mass is converted to a form of an energy or energy to a form of a mass. Therefore, the total of the mass energy before the reaction and after the reaction has to be same. And if the total, because this is a closed system, this is an isolated system. Therefore, they did found out that the total momentum before the process and after the process is also same. Because we are looking at the particles emitting with a specific speed. They have a mass. Therefore, the total momentum before and after is also same. So, coming back to the conclusion again, what are remains conserved during a decay process? It is the nuclear number, proton number, mass energy. What else I mentioned? Nuclear number, proton number, mass energy. What else remains constant? Momentum. Okay, momentum. So what will not be constant? I only mentioned one. Yeah? What is not constant before and after during a decay process? Nuclear or neutron? Nuclear, no. Nuclear number will remain constant. Neutron, neutron will change. Okay? So the nuclear number, the proton number, the mass energy, and the momentum of the particles that is involved, which is the parent nucleus and also daughter nucleus. Okay, so that will remain constant. So what will change is the neutron. So it's much more easier to remember what will not be constant because we only have one, which is the neutron. Okay, take note. So next is beta minus decay. So in a beta minus decay, you will notice that a neutron changes into a proton and an electron. So the electron is ejected from the nucleus. So you can see the explanation here. So a neutron is 1, 0. So 1, 0 neutron changes into a proton. So a proton that you have is 1, 1, which is also the hydrogen, plus an electron, which is 0, minus 1. So this electron is ejected from the nucleus. So the electron comes up from the nucleus. So before we have AZ, after that, you will have A, because then during beta decay, there will be no change in the nuclear number, only the proton number changes. So proton number becomes Z plus 1. Why Z plus 1 for the parent nucleus? Because during that process, electrons will be emitted. Already there will be a reduce of one proton number from the main nucleus. Therefore, it will be compensated by adding 1. So then this is what the complete equation will be. So a neutral nucleus decays So then it becomes a positive ion. Electrons will be emitted. So when you have one electron emitted, means one negative, it produces a positive ion, which is one positive. One positive, one negative, it becomes neutral again after the reaction. So before also neutral, after also neutral. So it must have the same state. It cannot be before neutral and after that it has a charge. It has to produce two particles which can neutral themselves. So when you write the beta decay for beta decay, which is beta minus, then this will be how you complete. Again, the rule of the atomic number, the proton number, the nuclear number, the proton number, the mass, energy, and the momentum are conserved. What changes is the neutrons. Okay. Beta plus. So for beta plus is opposite. A proton, you can see there is a proton, and this proton changes to a neutron. Just now neutron changes to a proton, now proton changes to a neutron. So in that case, I have electron negative positive produced, which is the positron. So a positron is ejected from the nucleus. So it's all a matter of how you balance the equation. So now when you have a positron, mean it produces 0 plus 1. So if I have 0 plus 1, I already have one extra neutron proton on my right hand side. Therefore, from the parent nucleus, the proton number I need to minus 1. So to compensate the plus 1 that comes in. That's all. So over here, you can see that during the practical, those who have already gone for the practical for the spectroscopy, we later probably I didn't mention, but I didn't want to go into detail because we don't cover that in detail in the syllabus. But in a way, when you talk about the inside, this is the diagram that you see is actually inside an atom. Inside an atom, there is different energy levels. So this is a nucleus and a center. And then you'll have okay. So you have your, and on the outer part, you'll have a, this whole thing is actually the atom. Okay, so you have the atoms. And inside you have the energy levels. The energy level is which is close to the nucleus, is known as the ground state. The furthest, which is close to the surface of the atom, okay, so where the electron can escape easily, that is we call it as the excited state. Okay, so the final state before the electron can leave the nucleus. So this is a ground state. What will happen? So during any process, you can see the electron, when gain energy, the electron can go to a higher energy level. They can go to a higher energy level. They can go to a higher energy level. And if they are not stable at a higher energy level, what will happen? They will drop to a lower energy level. This is what will happen when there is a energy absorbed and energy release. So we discussed about the emission spectrum and absorption spectrum. So when you say an emission spectrum is when electron from a higher energy level drop to a lower energy level is going to emit energy. And this energy that is emitted E equals to HF. That probably you have heard during the practical. So the energy emitted, so this is according to the Max Planck, a formula which is used to find the energy emitted by the wave. By the wave or when the transition of the electrons takes place. So that is whatever the wavelength that is, because we also understand this is supposed to be hc over lambda. So it is going to emit an energy of a particular frequency or wavelength. So you see an emission spectrum. But when an electron from the ground state or the, it's not necessarily from ground state, it can also go depends where is the electron. It can go from the second state to the third state, or that is, or from here. These are all are possible things can take place. So we will not go into detail about this, but it will give you an idea. These are specific energy: E1, HF1, E2, HF2. So when it absorbs a certain energy, what will happen? That particular frequency or wavelength will be missing because the particular coal gas have already absorbed it. Maybe we have used an hydrogen gas. So that particular wavelength will disappear from the spectrum. That is what we understand as the absorption spectrum. Because some of the wavelength has been absorbed by a medium when that particular continuous spectrum of light passes through. So when you talk about a spectrum, during the practical, you are given a catalog. It only had it only had two spectrum, absorption, emission spectrum. Okay, but for all sample, it is based on the observation when you use a white light. A white light is actually a continuous spectrum because it gives you all the range of wavelength from the 400 or 350 nanometer up to 700 nanometer, which is from violet up to the red. That is for the whole range of electromagnetic spectrum. So that one we call it as a continuous spectrum. So when this particular continuous spectrum, it is analyzed when it goes through a particular medium of gases and so on. That's why we have an emission and absorption spectrum comes in. Okay, so don't want to go into, because when you go into that, that's already another chapter in that. So at least you will know the idea of emission and absorption spectrum. And when you do any further readings, you will have able to pick up the what has been explained. So go back here. So we have excited state. Okay, so excited state means is the state where the electron has the highest energy level. The next moment, the electron is going to escape from the atom already. Then you have the lower energy level. It is the lowest. Okay, so where it can go here. It cannot go even lower than that. Okay, so it cannot go to the nucleus. Inside an atom, there is a different state of energy level. There is no intermediate state. Electrons can only settle at the particular energy level. It's just like you have a basement, I mean, this is the lower ground, first floor, second floor, third floor, correct? That are the energy level. Can you have 1.5 floor? Do you have 1.5 floor? No. You cannot go somewhere and try to stand in 1.5 floor. Cannot. There is no base for you to stand there. For the inside the atom, the electrons also like that. They have a specific energy level they can settle. They cannot settle in between. There is no ground for them to settle. So if they say the electron here excite all the way up to here, it has enough energy to come here, but then it cannot go to reach the next level. Then what will happen? It will fall back. It will still come back to the lower. Okay. So I know. Okay. So 1 minute. We'll give you the break. So gamma ray photon emitted. So during the the transition from a higher energy level to a lower energy level. A nucleon makes a quantum jump to a lower energy level. So use the word quantum. So this is what the quantum physics is about. So the jump is accompanied by the emission of photons. Photons are referred to the energy. When you refer to the formula E equals to hf, this is the formula that is used to explain about the energy emitted, energy carried by photons. So what are the photons? That one we will look into detail when it comes to the quantum physics. Okay, so you can just have a look. This we will take a short break. Okay. Yeah.
Вот пальбик, понял, в том числе деле, чем сводишь.
Okay, welcome back. Just to remind again, so on Thursday, replacement class 5:15 to 6:45. I will return the piece paper for you to check. Then I will collect it back. After that, anyone, if you ask, okay, to view, to know the marks, then you have to wait until the study week for the assessment marks to be released, the continuous assessment. I will not review that. So only Thursday. So you attend the session, you'll be able to see your marks. And anything further questions you have done, okay, you can ask. And if anything on the marks, okay, so you need to clarify, maybe I gave you extra marks, okay, so you don't want the extra marks, or if I have left out the marks to add up. So that one, after the class, you can wait to see me, then I'll update. Okay, so don't want to do that within the class, then it's going to track the lesson. So I want to spend maximum is half an hour possible, okay, so for the quiz related matters, then after that to resume with the class. Okay, let's continue. So we were talking about the radioactive decay process, nature. So we discussed about random decay and a spontaneous decay. then looked into the discussion about the emission and absorption spectrum in related to the transition of electrons inside the atom. But the transition of electrons inside this atom, not in the syllabus. But here, I just explained to you so that you have an idea of from where these particular energies are emitted or these particular energies are lost when they are absorbed and so on. Okay, over here, further when you refer to a radioactive decay, so next is from the alpha decay, beta decay, so now beta minus and beta plus, so now we go to the gamma decay. So just now we talk about beta plus and beta minus, so then gamma decay. So gamma decay, it is gives out just a photon. There is no change in any nuclear number or proton number of the daughter nucleus. So the parent nucleus and the daughter nucleus basically going to have the same nuclear number and the mass nuclear number and the proton number. But there will be some loss in the mass. So the loss in the mass is the one has been converted to a form of energy. Okay, E equals to mc squared. You can work out, you can calculate that. Okay. So this is one type of a gamma decay when electrons, you can see electron on an higher energy level drops to a lower energy level. Okay. Okay, sorry. So for the gamma decay, so this one indicates the electrons are dropping from a higher energy level. A transition, the actual word, I mean the exact word is the transition of electron from a higher energy level to a lower energy level. Therefore, there will be energy emitted. So it is emitted in the form of a gamma ray photon. Then, if you look at this is also a decay process stage from molonium, MO. Okay, so molonium to EC, titanium. Okay. So we no need to worry about all the names of the elements. So I'm not teaching the periodic table of your chemistry. So beta decay. So you have a beta minus emitted because it moves from a higher to a lower energy level. So excited state. So from excited state, it drops to the ground state. It emits the gamma decay. Oh, so from earlier one is the beta decay. So this is just to tell you when the transition takes place, energy will be emitted during the decay processes. So when you look at the equation, when you write for the gamma decay, therefore you don't see much difference between the parent nucleus and also the daughter nucleus in terms of the nuclear number and the proton number. So that remains the same. But there is a mass, so there is a loss in the mass, which has been converted to a form of energy, okay, which gives you the gamma ray. Okay. We have talked about this radioactive decay, which relates to the decay process gone through by the nucleus. If it is too light or too heavy, it has to go through a series of fusion and fission reactions in order for the nucleus to become stable. Okay. By becoming stable, the nucleus is able to increase the binding energy of the nucleus. So that is the the ultimate objective of the process, to increase the binding energy of the nucleus. Because we know binding energy is the measure of the stability of a nucleus. A nucleus, if it is stable, means it has a higher binding energy. You need more energy to break the nucleons to infinity, or to bring all the nucleons from infinity to form the nucleus. So the more energy that you need in order to form it, that means it is more stable. Okay. We talked about this graph in related to the stability region, line of stability. So over here, additional information given. If you look at the nuclei with excess neutrons can become more stable by beta minus decay. If they have too much of excess neutrons, so what will happen? It has to reduce the neutron number. So how to reduce the neutron number? So by going to a beta minus decay. So when you have beta minus decay, so therefore it is able to increase the neutron number so that the nucleus can move towards the right. Because you understand that during a beta minus decay, just now when you saw the beta minus decay, yeah. See, if you look at the beta minus decay, what happened? The proton number, you plus 1. So when you plus 1 means it is moving towards the right. So when you go to the graph, just now, it's not stable. So beta minus decay, the proton number plus 1. So plus 1 means it goes to the right. So if just say if it is too far from the stability, so probably it has to go through few times of beta minus decay in order for it to reach to the line of stability. So in a decay process, not necessarily they must go through one beta decay or one alpha decay. It can be a multiple beta or multiple alpha. It can be a multiple beta or multiple alpha until it reach to a stable region. Okay. So here you can see a series. To look at it, a decay series for uranium 235. A uranium 235 is heavy. So 235, the nuclear number is 235. Okay, and the proton number is 92. So therefore, from 235, 92 uranium, it decays, it becomes 90, 231 X. So it can go through series of process. So you can see for the first decay process, it emits one alpha particle. Okay, so which is plus 42 helium. Therefore, it has reduced 4 in the mass number. It reduced by 2 in the proton number. Then it has go through another alpha decay. So it can go through alpha decay, and it can also go through a alpha or beta decay here. Either way. So in that case, it is able to so one alpha, one beta, one alpha, one beta, one alpha, one beta. So until it reach to a lat 207, which is a stable. So you can see in the process here, how many how many beta decay have taken place, beta and alpha. Okay, if you have 1, 2, 3, 4. Okay, if you have 1, 2, 3, 4, 5, 6, 7, 8. Roughly about 8. You can just count. So 8 alpha decay and equivalent beta decay. So it has to go through a series until ultimately from 235 92 it can reduce up to 207 82. So you can see it goes all the way from 235 92 uranium to 207 82, which is lead. So it cannot just reach there by just emitting one particle or ray. So it has to go through a series. Okay. My battery is weak. Hold on, find that. Later I will upload this. Take a video. Yeah, make sure that all of your faces I can see. Yeah. Okay. And you want to show any sign? Okay, don't show inappropriate signs. Okay. You want to pose? You can pose. When I watch this video, probably I will fall asleep. Okay. Okay, thank you. Anisha, some face I didn't see Proctor in a. So it's right. I just want to check regulars. Okay, so not in class. Okay. So this one we have discussed. So move on. We have 4 more minutes. So radioactive decay, energy release. So here you can see a complete reaction. Okay, so between we have a paranucleus decays produce the alpha particle decay. There is an energy emitted. This energy can be calculated using the formula E equals to HF. And this is the daughter nucleus that is produced, whereby based on since is the alpha particle decay, so then the nuclear number is -4, the proton number is -2. Understanding of this important. Okay, so you will have a simple question related to that, and where you have to further use that to find the mass defect, and from the mass defect, so you need to find the energy that is released during the reaction by using E equals to mc squared. See, when it comes to relation, when you discuss about energy release, when we relate to the mass defect, obviously we must use the formula E equals to mc squared. You cannot use E equals to HF because E is HF does not have the mass defect. It only has the frequency and wavelength. So therefore, you must be smart enough when to use this equation. So when it comes to binding energy, finding based on the mass defect, obviously you have to use the formula E equals to mc squared. So here energy release. So energy release, we have a beta minus. So this is a process of beta minus. Again, same thing. You can find the, yeah, I forgot to touch on this. So in terms of nuclear masses of the nuclides, so you have mx, that is the nuclear mass of the nucleus X. Then my is the nuclear mass of the nucleus Y. And m alpha is the mass of alpha particle, nuclear mass, which is based on the helium nucleus. Therefore, mass loss during that alpha decay, it is the mass of the parent nucleus, which is mx, you minus the mass of nuclear mass. Okay, so plus the mass of the alpha particle. Okay, so the nuclear mass of the alpha particle. So when you find the difference, okay, so that will give you the, because if you look at it, you're supposed to basically find the difference. You take this mass, okay, so this mass, so mass of the parent nucleus, you minus Y and the alpha. So that will give you the difference in the mass that takes place, which has been emitted in the form of an energy. The same goes for the beta minus 2. Okay, so you have a beta minus, you have a beta plus. Please go through that. These all are based on a different reaction. So beta plus, beta minus. For gamma decay, nothing to worry because there is no loss in the mass. So whatever the energy that is emitted, it is in the form of gamma ray, and that energy can be calculated E equals to HF because there is no mass. So therefore, it is just based on the frequency and the or wavelength. Okay, the example 12, 13, 14. Okay, so we will be touching into the example tomorrow. Okay, before I further continue with the radioactive decay, which is related to the things that we discussed during the practical session 2. So this is a short part, just the formulas, then again it goes into the example discussion. Okay, and how we can, some things you can relate to the graph. Okay, and then about fusion and fission reaction, I already discussed. So I will just go through, glance through it, then we'll end the session. Okay, most likely we cannot finish it tomorrow. it will be brought to Friday, but in Friday, I will be able to complete this and brief you on the next chapter. Okay, so thank you.